Alright, so I had my microphone off, so we'll just do this a separate way. So please go ahead and pause this, and then we'll do these questions and we'll talk through them. Alright, so might not exactly go with the video, but number one, how many valence electrons are in the following? S, E, T, E, S, and O. And why was this not a hard question? Well, if you have your periodic table with you, the reason why this isn't a hard question is because all of those elements are in the same family. And as we know, valence electrons are equal to the family number. So if all the elements are in the exact same family, they'll have the exact same amount of valence electrons. And if I remember right now I'm talking and saying that that is the reason why elements in the same family have the same properties. That's because the valence electrons are the ones that will define the chemical properties as well, and that will explain that. All right, number two, place the following metals in order from most to least reactive. So we have lithium, and in this hour I had to explain, and maybe I didn't in your hour either, but the side-to-side rule for reactivity is more important than the up and down. So the most reactive one is lithium because it's the most left. Then barium and magnesium are in the same family. So then between those it would be the one that's lower, which is barium. And then the next one would be magnesium. And zinc, we circled that early because we knew for sure that zinc was the least reactive because it was way over towards the right. Now, when I asked the first hour class how they did, only 3 lab groups got this right. And that, was a red flag. So currently I'm explaining once again that anything more to the left, so family 1, everything in family 1 is more reactive than everything in family 2, and so forth and so on. All right, and we did have some data to support that. In the first day of class for part B, we added lithium, potassium, and sodium to water, and they were very reactive. The second day, we added things from family 2 to water, and they were not as reactive. They still reacted, but much less vigorously. So we do have some data to support the idea that everything in family 1 is more reactive. So to wrap it up once again, for metals, anything left is more reactive than anything right. And then if they're in the same family, then anything lower is more reactive than anything higher. Now we'll get to the third question here shortly. I'm not sure if I write anything. Okay, so here we go. In this one, it's the same idea, but it's the reverse rules. So nonmetals, if you remember, is higher and righter. So fluorine is in family 7. It's the highest in family 7, so it's definitely the most reactive. Then we move to anything that is next to its left, in its family, which is chlorine. We've taken care of those. Then we move to family 6. And if we have anything in family 6, we'll put that. And that would be oxygen. And then after oxygen, nitrogen and phosphorus are in the same family. So now it is the reverse of the metals. So the higher it is, the more reactive it is. And that would put nitrogen as the next most reactive element, with phosphorus being at the end. All right. Hopefully that kind of made sense. I asked here, and if I remember, 8 or 9 of the groups got that question correct. So one more time. Side to side for reactivity rules always wins versus up and down. So even though in family 1 lithium was very high and barium was at the very bottom, since lithium is in family 1, it will be more reactive than barium, which is in family 2. Then number 4, we obviously didn't really go over that answer. How do you feel about your understanding of the concepts in this class so far? Hopefully you feel comfortable with those and you're ready to go. There hasn't been a lot of concepts yet, but we're going to dive in now to the vagrant valence electron notes. And within the next 30 or so seconds, I'm going to realize my microphone was off the entire time. We might have a period of quiet. Just kind of wait, and it will come back on. Thank you for your patience. A second, and we'll see. Yeah, that whole bit was muted. Isn't that funny, Shay? Those kids will love it. Well, hey, welcome to the show, kids that are going to watch this. I'm Tom Davidson, and I'm an idiot. Okay, so anyway, we'll have fun. I'll just cut that for 6 minutes, and we're good. So let's talk about vagrant valence electrons. How far did we get? Oh, hey, first off, actually on page 4, there are 4 questions in the middle of the page. Will you take a minute and see if you can answer those? The 4 questions on page 4 in the middle of your page. It's above where it says vagrant valence electrons. That about right? Sweet, let's rock this party. So, vagrant valence electrons here on page number 4. Everything we've been doing has been leading us to this very moment. So I am pumped. Valence electrons are the electrons in the highest occupied energy level of an atom. Yesterday we had a quiz with 4 questions, and this hour did the worst on those last 4. And that's fine, I probably didn't stress it. You're not in trouble, I am. So, your valence electrons are equal to your family number. Did we ever say that in this hour? Okay, we did. All right, so all you have to do if you have your periodic table out is just find the family number. You look up top, you find the element just like the quiz we did with oxygen, sulfur, and whatever else. It has 6. We care about valence electrons because they're the only ones involved in chemical bonds. All right, electron dot structures show valence electrons as dots. Weird. So when we were going last trimester, we said dots were equal to family. Family is equal now to valence electrons. So dots must also be equal to valence electrons. It's a pretty simple idea. We all right with that? You can find that on your periodic table. Show your lab partner where to find where the family numbers are. All right, so our family numbers are found simply at the top. 1, 2, 3, 4, 5, 6, 7, 8. Now, if you had me, I had you put dots around those, remember? Perfect, Shani. Those dots also are equal to the family number, right? If you are sitting next to someone that had me, you can certainly do that. If you don't need to, you don't need to. That's fine. All right, next up. Electrons are shown as dots in the following diagram. So you're going to put those 1, 2, 3, 4, 5, 6, 7, 8s around your X that's there towards the bottom of page 4. All right, now, did any of you have a teacher that taught those different? All right, who did you guys have? Cullimore. How did he do it?
He just went like 1, 2, and then like 3, bottom 4, 5, 6, 7.
Okay, so his 2 were on top?
Yeah.
Okay, it really doesn't matter. As long as the first 2 were together, then you went 1, 1, 1, 1, 1, 1. It's fine. Now, what is going to be annoying is these are electron dot structures. In like 5 minutes, we're going to do what are called Lewis dot structures, and they're different. But a Lewis dot structure, for most people, you like it because it seems to actually make more sense. But anyway, this is how electron dots work, and this is why. It's because when you drew the boxes, you remember the 1 and then the 3 on top? The first 2 electrons always went together, and then when you moved up, you went 1 at a time until you had to pair. Seem familiar? So this box, and whether it's on top or not, it doesn't really matter, but the first are together, then 1, 1, 1, 2, 2, 2. All right. That button. Now, valence electrons are the only electron. Is that really where we're at? Yeah, it is. All right. I did some editing on this today. I'm worried I was out of order. Valence electrons are the only electrons used in formation of bonds, so they determine the chemical properties of an element. What class are we in? Chemistry. So our main concern is the chemical properties of elements. So our main concern from now on must have something to do with the valence electrons, because they will determine the chemical properties of an element, and they will determine how things bond, what they form, and why things are the way they are. So your whole life since like 2nd grade, you knew water was H2O, but you didn't know till today, most likely, that it's H2O because of the valence electrons in hydrogen and oxygen. All right, so I think just super quick, do these 5. I just want to double check. You can find the number of valence electrons. We refer to your periodic table over and over and over in Part B because it's super important that you can do this quickly. So all you're doing, just write them down somewhere. I don't really care where, but just how many valence electrons these will have, and then check with your labby. Do you think you're all caught up?
Oh, no, I was going to just try to be
Okay. All right, so these are just labs and demos, so just copy. Okay, that's nice of you. Okay, hold on. All right, here we go. So quickly, magnesium's in family 2. 2 dots if we want. Calcium is also in family 2, isn't it? Aluminum's in family 3, so it has 3 dots or 3 valence electrons. Sb is 4. I don't know, what family is that in? 5, all right, thank you. So 5, or 1, 2, 3, 4, 5. 5 valence electrons. And this is in family 4, isn't it? Okay. We all right with that? All you had to write was the number. Some of you, that's both. Nice call. My signature used to be 2 die. What people would say, let's see, I missed that part. Like, all it says is the number 2 and the word die. I'm like, no, it doesn't. It says Thomas Richard Davidson the fourth. Not really. But when I had to sign and buy my house, you have to use your full name, so I put a line right there. You know what that says? Thomas. It does. That's how. All right, moving on. Here we go. We've done that, we've done that, we've done that. All right, so what is the electron dot representation of SI? This is just the 3 things at the bottom. If you feel like we have beat this horse to death, I feel the same way. So put SI and then put how many dots around it? 5. Was that a trick question?
No, I put 5.
Well, there sort of are 5 if you count the dot above the I.
Yeah,
that's what Alec meant. He thinks at a higher level than you guys do. So SI is in family 4. So 1, 2, 3, 4. And he was just making a joke because he was counting that one, right? Yeah. That's usually my joke. He took it from me. All right, then. Hey, that looks familiar. Give the electron configuration for just the valence electrons of SI. Ooh, I don't know if we've ever done just the valence. So can you help me out? What row is silicon in? 3. It's in the 3rd row. So this whole thing of just the valence, we're going to start with a 3. Now, will everyone look at the periodic table? Silicon is in the far right area, right? Before I can get to silicon, if I go across the row, you have Na, Mg, and Al, right? So the way that it works, if you have me, you should know this. This chunk's called the S block. This is called the D. This is called the, what letter? Anyone remember? P. And these we don't really care about, but they're the F. So in order to know just the valence electron, you find the row, and you go across, and the first 2 were S's. So 3s2. And then you come across, and you don't get to silicon until you're the second one into the P. So 3p2. Now, if that didn't make sense, it's fine, because you never have to do that beyond today. But that's how you can find it for just the valence electrons. All right? You already have that written. If not, go ahead and write it. That's the answer to number 2. It's the part that's in the red. All right? So the valence electrons for family 7. So all you're going to do here, it just wants you to do this. 1, 2, 3, 4, 5, 6, 7. That's what it's looking for. And then we don't know what element we're talking about in family 7. So we will just put a blank S2 blank P5. How come I have a 2 and a 5 up top? Tell your lab partner. I know you know. Tell your lab partner why 2 and 5 are the numbers up top. Why are you here?
What? Just because we leave at 9 o'clock.
Okay. Well, welcome.
Thank you.
Get out of my room. Just kidding. All right. This is a 2 and this is a 5. How come, Packer? Because they add to 7, and we're talking about something in family 7. All right, good enough. Let's talk real stuff now. The octet rule. This is the top of page number 5. The octet rule will govern everything that we're going to do for the rest of this lab book. I keep saying that, but that's because each thing builds. All right. You could teach an entire year on this slide pretty much. Atoms react by changing, and the way they change their electrons, they will lose, gain, or share the number of electrons so as to acquire the stable electron structure of a noble gas. All right, so there's something I have to make for sure that you understand. When atoms react, they do not turn into noble gases. Will everyone repeat that to your lab partner? All right? Thank you. Now, not very many kids a year think that, but there's a few kids that think, hey, you add sodium to water, it reacts, it becomes neon. It doesn't, but its electron structure becomes like neons. So every one of us probably has a desire in our life to be financially stable and even rich. Would you agree to that? I would love to. I've probably said this in this class before. I don't really have that option. I'm a driver's ed teacher, track coach, announcer, and I don't make very much money. For a teacher, actually, I make a ton. But I'll never be rich. I will not ever be noble. Now, in electron land, in chemistry, every atom does have a chance to become noble. It becomes noble by either losing, gaining, or sharing electrons. And what we mean by noble is atoms will react, but if they're noble, they won't. Every atom wants to reach a stable state, and that's called a noble gas. Who's with me so far? All right. Now, yesterday we wrote a little periodic table, and I used a word that some people think is a little bit negative when I was referring to metals. Does anyone remember what I said about them? Metals are, maybe I didn't say it this hour, losers. Sad. Poor guys. Probably got swirlies in junior high, right? Metals are losers. Now, when we talk about losing, gaining, or sharing, what are we talking about? Starts with an E. Electrons. Thank you. So our metals, which are all of these things, they are defined as metals because they're losers. They lose electrons in chemical reactions. Well, what's the other side of the coin then? What do we call these? All right, they will be gainers. Non-metals are gainers. And then we always have like your tweeners right here. They're like, I don't know, I can lose or gain. I don't care. Do whatever you want me to do. Like, that's kind of cool and useless. Pick one side and stick with it. All right? So our non-metals are gainers. And we used this yesterday to say, hey, that explains why the rules reverse themselves. Does that not sound familiar? Maybe the bell rang earlier that I remember or not. But the lower and lefter we go, the better they are at what? Losing. Then the higher and righter, they must be the opposite of losing. So the higher and righter are better at gaining. Man, holy sleep. Just because I'm recording doesn't mean that you can't talk. They can't see you. They see this weird looking dude right there. Skinnier now. And they hear this. So please feel free to participate. All right. Here are why metals are losers. So we already talked about this a little bit. Well, let's just do sodium as my example. Sodium is what element number? Tell your lab partner. I demand that you talk.
That is sodium.
That is correct.
Yeah, what are we supposed to be doing?
Telling me the atomic number of sodium.
Sodium is
11. The answer was right there the whole time, sideways. It's 11. Yeah, whoa. So if I were to write its configuration, are you ready? Say yes. Yes, sweet. It'd be 1s2, 2s2, 2p6, 3s2. 1. I don't know why I wrote a 2. Just habit. All right, 3s1. Now, the closest noble gas to Na is where? Can you tell me? Neon. What's neon's atomic number? 10. Thank you, whoever said that. So Ne is 10. So that means, actually, let me write this. I'm going to put it right here. Ne equals 10. And I'm going to write its configuration in red. 1s2, 2s2, 2p6. And that's it, right? All right. The previous slide, we said every atom wants to become like a noble gas. So, how far away is sodium from being a noble gas? It's this piece right here, right? It has one too many electrons to feel good about itself. So it's going to go on a diet. And what's it going to do? It's going to lose it. All right? It's a pretty simple process. If sodium can kick that electron out, excuse me, kick that electron out, then it becomes the same electron configuration as neon. And even though it isn't noble, it can pretend it is the rest of its life. Who's with me? Who's with me? Who's with me? Okay. So it is to the advantage of sodium to lose an electron. It's a metal. It's a loser. All right. Can we all agree once again that this is neon's configuration? Okay. Let's look at fluorine. Fluorine is element number what? 9. So let's draw its configuration. I'll do that in green. It is 1s2, 2s2, 2p5. How close is fluorine to being noble? It's 1 away. It is 1 away. So what's it want to do? It wants to gain. Now, it can't just go and grab one from the sky. Where could fluorine get an electron? No. Good idea, though. It can get the one that sodium just kicked out. And once this gains 1, what does this number do, this 5? It becomes a 6. And now, look, all of these have the same electron configuration. All of them behave like they're a noble gas from now on. Now, neon is the only one that is a noble gas. The other two are pretending to be them by losing, that's my metal, and gaining, that's my non-metal. But by doing those two things, I have now reached what we call an octet. Tell your lab partner what an octet is in music, please. Because I put them next to each other and gave them a little bit of energy. And that electron just jumps. Fluorine is extremely attractive, and we're going to learn that term in a minute, to electrons. Sodium is not. So it's like, heck no. It's almost like that electron has been dating someone ugly, and then you walk by someone really good looking. And they're like, why would I hang out with you? All right. What is an octet in music? A group of 8 notes, essentially, right? How many sides on an octagon? 8. Legs on an octopus? 8. I know, shut up. It's technically 6 with 2 arms. I get that every year. I'm like, screw you. There's 8 things coming out. I didn't say screw you on video, did I? I didn't mean to. I apologize. All right, now, 8, correct? Please look where the 8, the octet rule, is coming from. Well, do you already know? Maybe you and your lab partner have a discussion of where the 8 is coming from this picture. Where's the octet? Talk real quick. If you don't know, it's fine. If you'll just usually listen to Alec talk louder than everyone, you'll get the answer. Sometimes you're wrong, but most of the time he's right. So what did Alex say? 2 plus 6 is 8. So look, this is the octet rule. It's saying that the valence electrons equal 8. As long as we have that, we have the octet. Good enough? All right, now, let's move on. And look, everything you're going to see in the next couple of slides we already just said, but whatever. Each noble gas, with the exception of helium, has 8 electrons in its highest energy level. Now, look right here. What's the 2-word term we use to describe in its highest energy level? Valence electrons. Each noble gas, with the exception of helium, has 8 valence. Why am I putting it there? There's the word electrons right there. Valence electrons. Because remember, valence electrons means in its highest energy level. Every noble gas except for helium. Helium's the weirdie, right? It's on the top row. He is in family 8. Could be a she. I apologize. It doesn't actually have to identify its gender. But this thing right here, it is in family 8. But really, it only has 2. Why does it fit, though, in family 8? Because it is a noble gas. That, by the way, is the reason why when you inhale helium to be funny, it doesn't kill you. Now, it can. If you overdose on it, you run out of oxygen. But it's a completely harmless gas because it's a noble gas. If you found, if you found a balloon full of chlorine, fluorine, bromine, iodine, and huffed that in, muerto in like 10 seconds. That means dead, yes.
My mom told me if I sucked in helium, it would kill my brain cells.
Okay, no, here. When you take a breath, we're taking in oxygen, which goes into our blood, which eventually goes to our brain. I'm not a human bio teacher, but I'm pretty sure I got this part right. All right? Your cells need to breathe oxygen to function. When you breathe in a lot of helium, you starve your cells of oxygen, and they can die. Your mom's not lying. Yeah, but if you're like taking half a balloon and then another half, like in the next 2 minutes to be funny, you'll be fine. You got way more damage. Did you grow up as a soccer player at all?
What?
Did you ever play soccer?
No.
Football?
Not really.
Okay, well, more brain cells die in one collision than they do in sucking in a helium balloon. All right. Who's with me so far? Good. All right. Ooh, I don't want to talk about electronegativity yet, but I will soon. If you've had Bert, it's what he calls the hotness factor. All right. So here we go. The octet rule and valence electrons explains the formula of H2O. You ready? You've always known that water was 2 H's and 1 O. And have you ever thought why? Who's thought why is it a 2-to-1 ratio? Well, that's sad. Think more, play on your phone less. There's your lesson for the day. All right, if I were to draw the electron configuration for hydrogen, what would it look like? Ooh, nailed it. 1s1. If I were to draw the box, it would look like this, right? All right, what would oxygen look like?
1s1, and 1s2, 2s1, 5.
2p4. Is this an octet?
No.
Does 2 plus 4 equal 8? No. 2 plus 4 plus what equals 8? 2, correct? But look at a hydrogen. What does it have? It only has 1. So if oxygen and hydrogen were to hang out, they only hang out in one way. You need 2 of these 1s1s and 1, give me a second. And 1 of these. This is oxygen. 1s2, 2s2, 2p4. 1, 2, 3, 4. You with me? All right, now I don't know if this will work, but you need this. Oh, it's all together. That's fine. I can do this because I can. To go right there. And you need that. Sweet. What do I need it? We'll just put it right there. To go right there. And can you now see that all the boxes are filled for oxygen? Yeah. Can you now see that for both hydrogens, both its boxes now have 2, or both of each one of its boxes have 2? Can you see it? Go ahead.
Is it possible to have more than 2 check marks in it?
No. Why? That's called the Hund rule. The Hund rule from last try said the maximum spin can either be a half or 0, but you can't have 1 1/2, which is weird. Like, what does that have to do with anything? It's just a fundamental law of nature. Like gravity goes down instead of up. We can't ever have 2. We can have 1 or 2, but never more. Now, we do have H3O. That is a thing. But H3O is a plus, which means one of your atoms doesn't have all of its electrons. Okay, now, an easier way, because this is kind of a pain to draw, isn't it? An easier way to do this would just be to draw the dots. How many dots does hydrogen have? 1. How many dots does oxygen have? 6. 1, 2, 3, 4, 5, 6. How many dots does it want if it wants an octet? 8. So it can take 1 hydrogen and share over here. Well, that sucks, whatever. Okay. I can do that. It's going to take this hydrogen's electron and put it right there. And now they'll share that electron. Now, how come hydrogen isn't losing it? That's true. That is actually the truer answer, but not the one I'm looking for. Hydrogen is not a loser because hydrogen is not a metal. Okay? But yeah, you actually went deeper, and that was the right answer. Is oxygen happy now? Happier. Is it the happiest? No, because it needs another H with 1 more dot. Then its octet is complete, and we now have H2O. Okay, this is under your octet rule notes. So you have an H plus an H plus an O. So you put 1 dot, 6 dots, and then you draw the new one with 8 dots around the O. So it should look like this. And then is it an arrow or is it an equal sign? Equal. Now, there's another one. Will you try that on your own? But I do need to tell you something. When we do these type of structures, don't write it in pen yet. Oh, you're in trouble already. When we do these type of structures, we use what's called a Lewis dot structure, where carbon typically is 1, 2, 3, 4. But in a reaction, please look, in a reaction, carbon, the first thing that happens is it absorbs energy and it promotes one of its electrons here. The reason it does that is so it can now bond in 4 places. Because carbon can't complete its octet with some things unless it can bond in 4 places, and this is one. So will you now try? All right, this structure, this is CH4. That's called methane, and that's what we burn when we burn natural gas or our Bunsen burners. Or it's also something that is released from your body that no one appreciates. So anyway, it will be explained why there are 4 H's, because to complete the octet on carbon, we need an H with 1, an H with 1, an H with 1, and an H with 1. Okay, let's do one more. Does anyone know the formula of salt? NaCl. Are there any numbers in that? No. And there's a reason why there isn't. How many dots does Na have? Na.
1, 2.
Sorry. I'm saying Na, but in my mind I'm thinking Cl. Na has 1. Just.
He's like, wait, you're all stupid.
Yeah, I'm like, why are you getting this wrong? Oh yeah, because I'm dumb. All right, Na has 1 dot. How many does chlorine have? 7, which is what I thought was coming out of my mouth. 1, 2, 3, 4, 5, 6, 7. So the octet for chlorine is filled by gaining. The octet for sodium is filled by what? Losing. Losing team, winning team. That was hard to write loser while saying losing, whatever. We sort of all right? All right. Now, once in a while, it gets a little weird. What if we have magnesium chloride? How did that go to an eraser? Now life's a little bit weird. Should we quit?
Yeah.
No, we have 6 more minutes left. All right. How many dots does chlorine have? 7. Thank you. 1, 2, 3, 4, 5, 6, 7. If you're annoyed how I'm writing the dots, just deal with it. All right. Now, how many dots does magnesium have? 2. 1, 2. So what will happen? Anyone? The octet is not filled. What? Is it an acid? Is that what you said? No. What? Say it louder. It needs a second chlorine. So right over here, Cl with how many dots? 7. 1, 2, 3, 4, 5, 6, 7. Now, if we look, chlorine has 8, correct? How many does this chlorine have? 8. How many does the magnesium have? 0, which means it does have 8, but it's the 8 below it, because it was a loser. No, it's still there. Still there. Now, if you want to watch this happen, right? Because chemistry's cooler when you demonstrate things. What I want you to do, I want you to come up with the electron, or it's called the Lewis structure. When magnesium and oxygen put Mg and O together like that, and I want you to come up with the dot structure. If there's more Mg's or O's needed, please add them, and I'll go get some magnesium, and we'll react with oxygen. know what's happening. Oh boy. All right. So what I'm going to do, this is pretty long, so I'm going to cut it in half, and then I'm going to light it on fire. When we burn stuff, we're really just reacting it with oxygen. That was almost messy. Move that away, that would be bad. All right, now, do not, and you might have already seen this. We used this demo a few times, and I can't remember if I did this year, but don't stare at it. Okay, so simply I'm taking magnesium, and it's a metal, right? So the magnesium is currently losing electrons and giving it where? To oxygen. To form what? MgO, right? The MgO, if I can do it. There we go. The MgO is right there now, right? Nothing metallic. What's that? Yes, it is. If only chemistry worked that way. So now I've taken a metal, I've taken oxygen, and I've created this powder, which is magnesium oxide. When you did the dots, did you need anything extra?
No.
Magnesium gave 2, oxygen needed 2, and they lived happily ever after in their noble mansion. I feel like you're done listening to me. I will not see you again until Monday.
Are you kidding me, Davidson?
Do I look like I'm kidding you?
Where are you going?
I'm going to Arizona.